Okay, welcome back to AP Pre-Calculus. Today we're going to talk about the assignment Change in Tandem 5. We talked about this assignment in lab on Tuesday, but I understand that not everyone was present for that. So I wanted to go over and just talk about what I discussed in that lab. Um, so this lab this assignment discusses concavity. So for concavity, first, we have to discuss what that is. Um, so, let's just start off with what we have for concave up. So, concave up is when any open interval on our graph is shaped like this. And we have concave down when it is shaped like this. So intuitively, that's just what our graph looks like when it's concave up or concave down. And our graphs can be a combination of those shapes. So if we have a cubic that looks like this, then part of our graph from right here to right here at this dot looks like it's concave down, and from here to here, it looks like it's concave up. But what is our formal definition for that? So we have an intuitive idea of what a concave up and concave down looks like. Um, what's happening here? Well, let's first look at the slopes of this graph as we move in the positive x direction for concave up. So if I look at the slope of this graph right here, the slope is angled downwards like this. I could say that m is equal to, I don't know, -4 right there. And maybe over here, it's still downwards, but the slope is less steep. So it started like that, and now it's less steep. And maybe here, m is equal to -2. And right here, less steep, m is equal to -1. And here at the bottom, now it's flat. We'd say m is equal to 0. It doesn't have any slope. And then, over here, now m is equal to +1. Over here, m is equal to +2. Over here, m is equal to +4. So, as we move in the positive x direction, the slope of our graph is increasing. It starts with a negative number, so -4, -2, -1, 0, 1, 2, 4. It's increasing. And we could say that the slope, so associate slope with our rate of change. We say that our rate of change is increasing on this interval. And for concave down, it's the other way around. So if we, again, as we move in the positive x direction, here, our slope might be +4 right here. It looks like the same slope that's over here. But over here, our slope may be now 2. And over here, our slope might be 1. And over here at the top, it's flat. So our slope is 0. And now over here, as we move over to the right, now it's angled downwards. So our slope is now -1. And of course, these are all just kind of approximations. M is equal to -2. M is equal to -4. And so, as we move in the positive x direction, our slope goes from 4 to 1, 0, -1, -2, -4. These numbers are decreasing as we move to the right. So, our rate of change is decreasing. So, concave up is when our rate of change, as we move in the positive x direction, is increasing. And concave down is when our rate of change is decreasing. And so now, when we're talking about concave up or concave down, we just need to specify what interval our graph is either one of these. And so, I think it's now appropriate for us to start looking at examples. So, if we look at example 1 here, we have a parabola modeled by this function here. And we see that our slopes, I'm going to use a red pen. And in fact, I'll use a green. Our slopes, say right here, well, first we can just compare it to what did our concave up and down look like. This is clearly concave up, if we look at number 1. But again, we look at our slopes, and our slopes, as we move to the positive x direction, increase. Now, I'm sorry, I didn't draw this too well here. So maybe you can't tell that well as we get further up the graph, but our slope, especially here towards the bottom, it becomes apparent, starts increasing. And so we start off with a negative slope over here, and it starts becoming flatter and flatter and flatter and positive. And so this is how we justify that as concave up. It is that our slopes are increasing for this function. And so what we want to do is just say, where is this function concave up? Well, it's not a trick question. This function continues to behave the way we see it, where these arrows say they do. So it just keeps on going up and up and up and up. And over here as well, just keeps going. We would say that this is concave up on the interval from -infinity all the way to positive infinity. And when we give intervals of concavity, these are always our x coordinates here. We don't pay attention to what the y coordinates are. We're just saying that as we start all the way out here from -infinity all the way to positive infinity, it is always concave up. It doesn't matter, even though we can't see the graph as it behaves off page. It never changes direction like that. So all the way from -infinity to positive infinity, it is concave up. So what about our second example here for number 3? Well, as I mentioned before, we can have concave up and down on the same graph. And so, let's look at our slopes. So in red, I'm going to use for concave down. But our slopes here, so it starts off positive, and it starts decreasing. And so we have very, very positive slope here, And as we get further and further, it tapers off to become 0, and then it starts decreasing. So we started increasing, and now it's decreasing. However, right here at this point, and I'm going to mark it in black, right here at that point, our graph actually transitions to being concave up because the slopes now starts off negative, then it becomes flat where it's 0, and now becomes positive again, so it starts increasing. So we have negative slope, then a slope of 0, and now our slopes start increasing again. And similar to the last problem, it's not a trick question. It continues to be concave down over here, and it continues to be concave up over here. And so I could say that this is concave up on the interval from whatever the x coordinate is here. So our transition point, the x coordinate of our transition from concave down to concave up is -1, so it's -1 to positive infinity. And then it's concave down from negative infinity to, oh, why did I write -1 there? Sorry about that. +1, +1, +1. And so concave down from negative infinity to +1, like that. And anytime we're talking about intervals of concavity, and similar to continuity, these are always open intervals. So you never have to use square brackets to distinguish between whether it includes some point or not. These are always going to be open intervals, so we will always use parentheses. So that's how we can do this example. Let's look at the next one. So for number 5, okay. So we see that along this, if we just start from the left, we have negative slope here, and as we move further and further along, it becomes more and more flat. It starts flattening out until it becomes completely flat right here. And then it starts increasing, and we get a positive slope. So we start with a negative slope, 0, positive slope. So that is concave down. I'm sorry, concave up. Our slopes are increasing. We start with negative, 0, then positive. So all the way to the x coordinate right here where it transitions, because now the slopes start, they're positive, and right here at x equals 3, our slope is equal to 0, and then it becomes negative. So we have positive slope, 0 slope, and the negative slope, our slope starts decreasing, so that is concave down right there. So using my pens, I'll use green for concave up. So our slope is increasing along there, and our slopes are decreasing along there. And so it transitions right where x is equal to 2. And we say that this is concave up on the interval from negative infinity all the way up to 2. And it is concave down from 2 to positive infinity. Let's look at number 7 now. So This isn't a polynomial. However, to distinguish whether it is concave up or concave down, let's just look at our slopes. So right here, our slope starts very, kind of steep right there. And then as we move further along, the slope gets flatter and flatter. And now it never gets quite completely flat. It starts off moderately negative, and then it approaches zero. So it's increasing. We start with a slope that is pretty close to -1 here. And over here, we get a slope that is maybe closer to -1/2 or so. And so that is concave up. Our slopes are increasing. So if I use green just to stay consistent, we would say that this is concave up. And I start writing down, of course, but concave up on the interval from x coordinate of 0 all the way to positive infinity. Let's look at the next one. Okay, so similar to the last one, our slopes, just starting over here, kind of flat, but negative. And as we move further along, they get more and more negative. In fact, as we get closer to 0 over here, now it's becoming kind of steep, so pretty negative. So we start off with close to 0 over here, and then pretty negative over here. It's decreasing. So this is concave down because our slopes are decreasing as we move to the right. So give kind of a visual there. We have, and to make it a little more accurate, just because this one has pretty visually consistent slopes there. But start off kind of flat but negative, and as we move along, it just gets more and more negative. And so we would say that this is concave down from -infinity to 0. Our x coordinate right here, 0 where the function cuts off, and -infinity because it just keeps going that way. Now what about this one? Okay, well, let's look at concave up and down. So let's look at these charts again. It might be tempting to say that this looks concave down. And as tempting as it might be for that, remember that concave down and up, concavity is a measure of how the rate of change or the slopes are increasing or decreasing. So if we start over here, our slope, in fact, we could say that right here, just looking at our function, our slope is exactly +3 right here. But it's also +3 right there. And it's also +3 right there. So it's not changing right here. It's not increasing. It's not decreasing. The slope is the same along this entire stretch of the function. And then over on the other side, it changes abruptly here at x equals 0. But then it's negative, but -3 every single point. So again, the slope is not changing at all. So this function is neither concave up or concave down. So we can't assign an interval of concavity to this function because the slopes aren't changing. Uh, so we can't say it's either. Okay, what about the next one? Okay, so just starting from the left, we have a sort of flat but positive slope here. And as we move further and further to the right, it levels off and becomes completely flat right here. And then it starts to become negative. So we start off with positive, then negative, I'm sorry, positive, 0, negative, really, really negative over here. So our slopes are decreasing as we move to the right. And then over here, it transitions right along this vertical asymptote. Remember, vertical asymptotes are just these dotted lines that our functions do not touch. As soon as we pass the vertical asymptote, now we have really negative slope that starts to level off. It becomes completely flat right here. And then it starts increasing. So we have negative, then 0 slope, positive slope. So it's increasing along here. So over here, we have decreasing slopes. So concave down from negative infinity to all the way to 1. So this x coordinate of 1 here. And then we have concave up along this stretch here. We start off with negative slopes, and then it becomes flat, and then we get positive slopes. So concave up from 1 to positive infinity. Let's look at something a little crazier. Let's look at number 15. So with number 15, same idea. We have our function barely discernible, almost completely flat, but not quite. Negative slope. And as we move further and further to the right, it becomes more and more negative, so it's decreasing in slope. So our slope is decreasing along that interval. And over here, our slope starts off very negative, and it starts to taper off and become flatter and flatter until it reaches 0, approximately right there. And then it starts increasing, and it just shoots off like that, positive towards the positive value. So negative, 0, positive, our slope is increasing. So we would say that this is concave up. And finally here, our slopes start off very, very positive, and then they start decreasing until they approach 0 over here. So it starts off really really positive, and then gets really close to 0 over here. So it's decreasing again. So this is concave down. So you say concave up on this interval from negative 2 to positive 3. How do we say concave down? We have two separate intervals. Fortunately, we can use our set union symbol, so concave down. It's concave down from negative infinity to negative 2. And since it is also concave down over here, all we have to do is just put a union symbol. It looks like a U. And then we have from 3 to positive infinity. Like that. And so now, these are our intervals of concavity. Let's look at the next one. Okay. So let's start from over here from the right. So we have a slight negative slope here. And maybe hard to tell, but it starts increasing until it becomes flat around right there. And then it shoots off towards positive infinity here. The slopes just become really, really, really positive there. So we start off with negative slope, 0, then positive slope. We have concave up here. And over here, our slopes start off really positive, and then they become flat right here, and then negative slope. So positive, 0, negative, slopes are decreasing, so it is concave down. So concave up here, concave down here. The only issue now is this hole that we have in our graph. So our function is not defined at this hole. So it is concave up along this whole interval here, except right here. We can't say that it's concave up or down right there. So anytime we have a hole in our graph, we just jump over it. So we say that this is concave up from negative infinity all the way to 0. Jump over that with a union symbol. And start on the other side of 0 again. So we're just skipping over 0. And then it's concave up all the way until 3. And we are concave down from 3 all the way to positive infinity. So for the last set of examples that we have, I'm going to highlight the intervals where these functions are concave up or concave down. So these functions might look a little crazy. And the reason that I want us to highlight them instead of just specifying the intervals is because these functions, despite the arrows implying that they would just keep going in that direction, or this would, just taper off in this direction somewhere, these functions actually keep on repeating like this. We'll look at these more next semester when we talk about trigonometry. They have a property called being periodic. So I figured it would be easier if we just highlight the intervals where they're concave up and down. So concave down, I'm holding my red pen, so I'll just do that one first. And it's this shape where it just looks like a hill or something. So if I highlight where it's concave down, it'd be right here. Because then, look, right here starts to become concave up. And so this would also be concave down. and this would also be concave down, and this would also be concave down, and sure enough, this part is concave down as well. So all of that is concave down. And all of this over here is concave up. So concave up and concave down. Next page here. Looks a little crazy, but if we highlight where it's concave down, would be right here, and also right here. It'd be concave up along these intervals here. And for the last one, I think this one's pretty easy. Concave down, right here, and right here. And concave up, right there, and right there. And so, that concludes all of the examples for this assignment. So thank you for watching.